So, let me start with this. One of the meanings of the background independence of general relativity is that in order to meaningfully describe the gravitational field, we need to use internal coordinates. By this I mean we need to use some internal degrees of freedom to describe the values of other fields with respect to these coordinates. And in particular, if you are interested in the dynamics of the gravitational field, you have to rely on the internal time coordinate or internal clock. And in many cases, there are plenty of good internal clocks, but none is preferred. So we need to understand the relation between dynamics, which is given in different clocks. And I mean quantum dynamics, because there should be no problem and no difference between different classical dynamics in different, the same dynamics, classical dynamics given in different clocks. The problem is that in canonical general relativity, the Hamiltonian is a constraint, and it means that dynamics is a gauge transformation as well, and these dynamical observables are not gauge invariant. So, so the question is, are there any dynamical properties which do not depend on gauge, which in this case means on the choice of internal clock? Or even put more strongly, does quantum gravity in internal clock make any dynamical predictions at all? It is a reasonable question to ask. I'm not going to give even a partial review of what was done before, but let me just point to three things which might be useful to keep in mind while listening to this talk. So the first reference to the fact that you have to work with internal clocks, and probably canonical formalism based on different internal clocks are not canonically equivalent, so there will be some non-unitarity in transformations between these two descriptions. I found in this in a paper by Anovides and Misner, if I remember correctly, it's called Generalized Uncertainty, Heisenberg Uncertainty Principle. The first, as far as I know, the first person who systematically studied these differences between different clock-based quantum dynamics was Kukash, but he concluded that this dynamics must be based in completely different Hilbert spaces, and there is no meaningful way to make any comparison. Since then, there were many other interesting studies by Hajicek, then by Kijowski, very recently by Martin Boyowald. But I'm not saying that this is a prevailing view, but it's a view shared by many people, which I found in the Timmans textbook, which says that, well, at the end, the differences, surely there are some differences between different clocks, but they must be physically irrelevant. And one of the arguments is that otherwise we wouldn't simply make any sense out of it. So in this talk, I'm going to dispute this position. So first I will start with definition of the time problem, because time problem, there are many aspects and many perspectives, so I will take maybe a very specific perspective on this problem. I will define it. Then I will discuss the concepts of internal clock and formulate the theory of transformations between different internal clocks in the canonical formalism. Then I will implement this theory in the quantum formalism, as canonical transformations are implemented, at least some of them are implemented in terms of unitary transformations. And this formulation, I will call it internal clock formulation of quantum mechanics. And then I will apply this formalism to some well-known cosmological systems and see what one gets. I must say that what I was trying to publish when I was results concerning the general formalism, the review process went very smoothly, but as soon as I tried to apply it to specific models, which was quite a simple job because it was just, specifying quantities in the formalism and obtaining very strange things, maybe at first, in this results concerning these models. There was a strong resistance from referees, so it was very controversial according to some referees. But it was a logical implication of the general formalism. So if I would be more than happy if I would provoke a debate with this talk. Okay, so just let me say that again. Repeat that in general relativity, the Hamiltonian is a constraint. It's a sum of in the ADM formalism. It's a sum of 4 first-class constraints. The constraints are functions of the free metric and canonical conjugate momenta, which are proportional to extrinsic curvature. They are first class, and they generate gauge diffeomorphism. They generate diffeomorphism. The so-called diffeomorphism or vector constraints generate the spatial diffeomorphism, and the scalar constraint generates on the constraint surface, obviously. So this means this means weak inequality on the constraint surface generates a time-like diffeomorphism. So the Hamiltonian H is a generator of gauge transformation and a generator of the dynamics at the same time. According to the usual interpretation, the physical variables, also the Dirac, the physical variables are gauge invariant. They are denoted by D, the Dirac observables. That means they commute with the constraint on the constraint surface. But if Hamiltonian is a constraint, then Dirac observables are constants of motions. But we have dynamics, so they alone cannot possibly describe the dynamics of the system. So we need to include some dynamical observables, and we need to equip them with some Poisson structure if we want to quantize them canonically. But here's the problem. Any extension of the space of physical observables, extension, so you want to add dynamical variables to this constants of motion, means the following obstacle. So what is a physical observable, you can say? You can see this any function on the constraint surface. So in fact, in this kinematical phase space formulation, this is an equivalence class of functions which are weakly equal, that is, which are equal on the constraint surface, because anything which happens beyond the surface is physically irrelevant. Then you ask what is the Poisson bracket. But the Poisson bracket between these equivalent classes. So it means that on the constraint surface, the Poisson bracket between any two representative, you take two classes, and you can take any representative of each class, and you compute the commutation relation, and you will find that the Poisson bracket is well defined only if these representatives satisfy this condition. That is, they are Dirac observables. So the Hamiltonian constraint formalism gives you a Poisson structure only for Dirac observables, not for dynamical observables. So let's take a more geometric view on this system. So we have a kinematical phase space, we have a constraint surface which is given by this constraint function, and we have a vector field Hamiltonian vector field generated by this constraint function. Now, the induced two, and you have a symplectic form. The induced two form on the constraint surface, which I denote by this, is degenerate, and the null direction is the null vector field of this two form is exactly given by the Hamiltonian vector Hamiltonian vector field. So it's actually a complete characterization, almost complete characterization of the system. So now we want on this constraint surface we want to introduce we want to consider all functions as observables. All functions, not only those which are so this is the again the orbits, the gauge or dynamical orbit generated by this Hamiltonian vector field, and we want to consider all functions, not only those which are invariant with respect to this, but only also dynamical ones, and equip them with some Poisson structure. There is one thing which we should observe is so the space of this orbit can be identified with the space of Dirac observables, yes, because they don't vary along the orbits, and you can define a Dirac bracket or a symplectic structure on this space, and there is a canonical symplectomorphism, a canonical isomorphism or symplectomorphism between this space and any gauge fixing surface, that is a surface that crosses each orbit once and only once, and the canonical structure is given by this induced form restricted further to this surface. But it's a basic property of gauge systems. It simply says that there is a canonical isomorphism between different gauge fixings, and between these gauge fixings and the space of Dirac observables. So this will this allows people to turn constraint surface into the contact manifold, which is the object which appears in unconstrained dynamics, and this is called the reduced phase space approach. So how it works? People introduce an internal clock, which is a function on the constraint surface, which varies along the orbits, and at each level set of this clock, they confine to each level set of this clock. They confine this induced form, and then it becomes invertible. So they invert it, and they obtain a Poisson bracket on this surface, gauge fixing surface, and they repeat it smoothly for all clocks. In this way, they define a Poisson bracket in the constraint surface, so they can commute any function on the constraint surface with any other function on the surface. But of course, this procedure is ambiguous. So there are many good internal clocks. But and there exists a decomposition of this two form. So it's of this induced two form into the part which is obtained by confining it to a given surface which crosses a given point, plus the rest. This is a closed two form. This is a closed two form. This must be a closed two form. It must be because this thing is confined to the surface, t equal constant. So this must be proportional. The rest must be proportional to dt, and it's closed. So there must be some function which is called, and the function is called Hamiltonian. So this can be decomposed as this part plus this part. So this already resembles the Hamilton-Jacobi theory. So in Hamilton theory, you have you talk about contact manifolds. So dynamics. So you're talking about manifold, which can be foliated into a real line times a lower dimensional manifold, and this is called a phase space, and this is called a time manifold. So here, with the use of this internal clock, we have managed to obtain, a usual formulation of classical mechanics with the contact manifold, and this null vector field, Hamiltonian vector field, generates trajectories, and the trajectories can be found by solving the respective Hamilton equations. So they will give me the trajectories will be expressed in this internal clock. So at this point, you might think that the reduced phase space just reduces the initial Hamiltonian constant formulation to a usual system. But there are two important differences. First of all, the value of your clock is very important to reconstruct the state of the system. It's not some absolute external clock whose value is completely irrelevant for specifying the state of the system. It has to be if you have to reconstruct the geometry, for example. Another difference is that you can choose another internal clock, and you will obtain different slicings. So there will be what you call a phase space will be a different slicing of the constraints. So this will be different, canonically different formulations of the same dynamics. So we have to take into account this feature. And to do this, we have to extend the notion of canonical transformation. So what is a canonical transformation? Canonical transformation is a transformation of a phase space variables, Q and P, which can depend on T, but doesn't have to a new pair of canonical variables in such a way that the form of the contact form is preserved. But here you replace it with new canonical variables. H can possibly change, your Hamiltonian can possibly change if this transformation depends on T, and T is preserved by the transformation. It's a basic definition of what you mean by canonical transformation. So we need to extend this to include a clock transformation as well. And we will require that the form of the contact form will be preserved. So you obtain new contact, new canonical variables, new Hamiltonian, but also a new internal clock. And now, what is a canonical structure? You remember, in order to obtain a Poisson bracket, we have to confine this form, contact form, I can say, to a constant time submanifolds, and then invert it. So the symplectic form is this part, and it strongly depends on the choice of your internal clock. So with different choices of internal clock, you will have different canonical structures. So things which commuted in one clock may not commute in another. And with this property, we have to go to quantum theory. So the clock transformations form a group, and it turns out that the group of canonical transformations is a normal subgroup. So it has a structure of a fiber bundle, where the total space is the group of these transformations, pseudo transformations, and the fiber is the group of canonical transformations, and the base space is the space of clocks, you can say, which is the cosset set. And I assume it acts, that this group acts freely, actually the bigger group acts freely on the space of contact coordinates. Notice that I'm not saying canonical coordinates, I'm saying contact. That means that I add the internal clock as another coordinate, acts freely, so I can identify this structure with the space of contact coordinates. Now, how to study this canonical transformation, the pseudo-canonical transformations? It is enough to be focused on one set. Once you choose a clock, it is enough to focus on one choice of canonical coordinates, because all others are related just by the usual canonical transformations. You are not interested in them. So we want to define a cross-section that is a function from a space of clocks to the space of contact coordinates. It's a cross-section on this fiber bundle. And then we can, how to define it in a very convenient way. Well, first of all, we can require that the symplectic forms in the new variables will have this form. You see, there is no bar on H. So the Hamiltonian is formally the same. It would simplify things, because I would just simply reinterpret the variables and say, oh, it's the same system in the new variables, but I don't have to solve new equations. In fact, you can even require more. You can say that all Dirac observables have the same functional dependence on contact coordinates independently of your choice of internal clock. And when you combine, so you have 2n dimensional phase space, 2n plus 1 dimensional contact or constraint surface, dimensional constraint surface. So this relation, you add your relation for a new clock, which you define as you want, and then you obtain 2n plus 1 algebraic equations for 2n plus 1 new internal coordinates. So you have specified new. So it's like this way. You are given an internal clock. You specify some canonical coordinates for this clock, and then whatever clock you will point, a new clock you will point, the canonical coordinates associated with them will be easily derivable from this relation. Well, very quickly, free particle. The contact form is this way. QP canonical variables, H is the p square over 2. You can identify the Dirac observables, or constant of motions, which have this form, and when you apply this relation, you will find that if you define a new clock with this delay function, depending on QP, the new canonical variables have to have take this form. And the contact form will have exactly the same form, and Hamiltonian will also be the same. So formally, it looks like the same system. And it is the same system, but the meaning of the variables is different. Okay, so now I would like to incorporate the internal clock transformations in the quantum formalism. Are there any questions at this point?
Maybe I will overlook something. Which part of definition of your internal clock implies that this subgroup of transformation, the canonical transformation of this larger group, is normal subgroup? Because I think it's very important.
It's independent, because once you fix, you can look at it this way. Once you fix your internal clock, you just do canonical transformations, and you just change canonical coordinates, but you don't change the clock. And once you change, you can always.
Pseudo-canonical transformation, you have change of clock.
Yes, you have a change of clock. Yeah, I mean, it's a more general, but it includes such transformations which include a change of clock.
Okay.
The second Dirac observable for a particle depends on t.
Yes, it's because it's a coordinate on a constraint surface, and it's an observable. At the end, you need it to reconstruct the geometry and so on. But of course, if you plug, so here with this, there's associated some Poisson bracket, and if you plug this t, of course, it commutes with everything, like in the usual formulation. So what is the idea now? I want to quantize the theory in each set of these contact coordinates. One important, and then I want to compare. So one important thing that I want to do, I want to ensure that the usual ambiguities which you have, you quantize the same system in different theories, in different variables, and there are some other, usual ambiguities like ordering ambiguities and so on. And I want to ensure that any difference that I'm going to detect between the respective quantum dynamics arises due to the choice of clock and not due to other ambiguities. And how it can be ensured. Here I just define what I mean by quantization. Like I have to extract the basic property of the quantization, and it includes canonical quantization and much more quantizations. I find quantization, for example, but then with this extracting this basic property, then you can prove the following. I can demand that all Dirac observables or constants of motions are given by your quantization map are given the same operator irrespectively of in which clock you are working in. This is logical. This doesn't depend on clock. The structure, the canonical structure of this observable doesn't depend on clock because these are Dirac observables. So the canonical structure only depends on clock, only the canonical structure between dynamical observables. This is important. And in fact, if you put this requirement, impose this requirement, you will find that this specifies the quantization of the entire systems of all observables in all clocks. So you cannot impose anything more, and this is what you reasonably should impose in order to get rid of these ambiguities, which I told you about. So, if something is a Dirac observable, it will be mapped to the same operator. Remember, everything happens on a unique Hilbert space.
But it is not enough to get unitary equivalence between Hamiltonians, for example, and
Hamiltonian is just one Dirac observable, one constant of motion, but there are more. No, it's not. They won't be unitary equivalent, the theories, the full sets of observables, no. But if you are working with some observable, which is not a constant of motion, it will be mapped generally to a different operator in different clocks. And then you can, when you analyze the meaning of this result, you will arrive in something which I call internal clock formulation of quantum mechanics, which is a slight extension of the usual formulation, and which, this is the fourth, includes ordinary, as I will show you, as a very specific case, subcase. So what it says that a physical state is given by a vector, as usual, in a Hilbert space, independently of with which clock you are working and so on. The non-dynamical content of this vector is given by terms of wave functions. There are square integrable functions on spectra of some self-adjoint operators. And if the self-adjoint operator is a quantum Dirac observable, this wave function, the form of this wave function doesn't depend on your choice of clock. So this is a choice-independent content of the meaning of the state. Hamiltonian is a Dirac observable, so it doesn't depend on internal clock. So the Schrödinger equation is the same in all internal clocks. So the dynamics, but you're not talking about dynamics of the wave function, talking about dynamics of the states. Are the same in all internal clocks. It simply doesn't depend with which clock you depend. The curves, the solutions to the Schrödinger equations are the same. So dynamics is unique, but now the dynamical content, the dynamical interpretation of the states has to be obtained by self-adjoint dynamical operators, and these depend on the choice of internal clock. So if you decompose a given state with an operator corresponding to a given classical observable, it will depend on your choice of clock. Okay. And ordinary quantum mechanics can be obtained as a special case. So let's go back to the example of a particle, free particle on a line. So the contact form, the Hamiltonian p square. We do a clock transformation with this so-called delay function, and what we obtain? P is a Dirac observable, so it doesn't change under this transformation, because this is the requirement of the transformation. Q is not it's a dynamical observable, so it will change. Its form. So now in new coordinates, if you describe the same observable, but in new Q and P bar, you will have a different functional dependence of this observable, this initial position. The same with the operators. So for momentum of the particle, you will get the same momentum operator, the usual momentum operator, but what you will call the position operator will depend on the internal clock which you work with, and it is an operator which depends on D, yes, on the choice of delay function. If D is 0, you will get just Q, yes, but if D is non-zero, then you get something else. We analyze this, a maybe wider class of delay functions and transformations, but so let's take a state. Let's take a state, you can specify it as a wave function on the spectrum of the Dirac observable in momentum. So we define it in momentum, so there's a unique state. So we will take some Gaussians with some varying parameters. So here they are Gaussians, and but here you plot them as probability distributions on Q, yes? So you take the state, but you go now to the Q the position representation. And here you go to a new position representation, and you see what happens with the choice of clock, the spectrum of the position operator discretizes. So even the spectrum is a feature which strongly depends of the operator, which strongly depends on your choice of internal clock. The probability distribution doesn't change so drastically, but you see the discretization can be a matter of the choice of clock. And this is a very simple transformation.
This seems to be very dangerous because, for example, in some choice of internal clock, you can have hydrogen with continuum spectrum.
Energy, but energy is a Dirac observable. Its spectrum doesn't depend on the choice of clock. Now the limit. I told you that it includes the ordinary quantum mechanics. It's an extension. And here how I think about ordinary quantum mechanics within this formulation. You can say that the entire system can be decomposed into the two sets of degrees of freedom. And one set I will call internal system, and the other I will call internal observer. And then here I just model the system with motion of a free particle in higher dimensions. And you assume, first of all, that the degrees of freedom associated with the internal system have to be described at the fully quantum level, the quantum formalism, but the dynamics of this internal observer can be approximated by the classical formalism. That's what you assume. And then you restrict the clock transformations in such a way that your clock transformations involve only the variables associated with the internal observer described classically. Then, well, what you will find that, of course, you will get canonically inequivalent formulation, in particular for the observer, but from the classical point of view, it is completely irrelevant with which canonical structure you work with. But you will find that at the quantum level, it will lead simply to a relabeling of this. If you focus only on this internal system, a description of this internal system, it will just lead to. Let me maybe go back to the picture I have here. Oh yeah, like here. It will lead only to relabeling of the slices. It won't lead really to a change of internal clock from the point of view of the internal system. So it's like a change of units, maybe nonlinear transformation of units or something. So at the end you will get you will see there's a unitary transformation between descriptions in these different relabeled choices of internal clock. Okay. Now we go into the final part of my talk, that is to apply this to quantum cosmological systems. Maybe any questions at this point? So the idea is very simple. We'll follow the quantum dynamics of cosmological models with the expectation values of some operators, dynamical observables, because through non-dynamical we will see no dynamics at all. But then we will switch to a new internal clock and we will follow the same dynamics with the operators which corresponds to these observables with this new internal clock. Okay? Let's start with a Friedman model, spatial Friedman model. So this is the line element. We assume that it's filled with perfect fluid, anisotropic fluid. The constraint is of this form. So this PT is this it's very, here is very simple. So this is associated with the fluid. It's the constant momentum. It's associated with PT, and PT is associated with the fluid, and Q and P are the isotropic variables. Q is like volume, and P is like expansion rate. So this is the symplectic form. The unreduced, the kinematical phase space. So then what you do, you solve the constraint. So you induce this form on the constraint surface just by substituting PT with this H. So this is the contact manifold. So this should be minus. So we will describe the dynamics in minus T instead of T. So you have a reduced phase space formulation. You can identify the motions of, you can identify the constants of motion, the Dirac observables. You can consider some pseudo-canonical transformations of this type. Now, this is the classical dynamics of the model. Then you quantize the model and you look at the dynamics of the expectation values. And this is what you will see. Because this describes a particle on a half line, a free particle on a half line. If you quantize, so you will replace Hamiltonian with a minus Laplacian, so it will describe a wave which just reflects of the boundary. You have to fix a boundary condition, that is to say, with what is the shift of the phase of the given wave at which it reflects. And this gives you unitary dynamics. So there will be a bounce, a reflection. And if you describe it in this semi-classical term, you will see that there is some kind of smooth bounce. Okay? But now we will switch to other clocks.
Picture depends on the boundary condition.
This picture? Yeah. I don't think so. No. You see, here is so it's a generic. This will be like a semi-classical Hamiltonian, and you will generically get a semi-classical Hamiltonian of this form. The value of K may depend on boundary conditions, but it also depends on what function you use, wave function you use, and so on.
But is it a Dirichlet or Neumann?
I'm sorry?
What sort of boundary conditions? Do you see a Dirichlet, Neumann?
I think it doesn't depend. You will always see this kind of picture at the level of expectation values. Yeah, I mean, yeah. And then you repeat the same thing, but after you go to a new internal clock, and you see, and you look at the dynamics, and you see that by changing to making a certain transformation of clock, you can lower the bounce, lower the volumes at which the bounce happens. It's the same dynamics, but looked through a new internal clock. Or you can do the opposite. You can make such a choice that the bounce at which happens, so this is this, let's say, the repulsive potential, because here you see there's some kind of repulsive potential. So it repels the particle away from the boundary. So you can say amplify the potential and make the same trajectories, the same solutions to bounce at larger volumes. You can even make such a choice of internal clock that you will see more than one bounce, 3 bounces, 5 bounces, and so on. Or you can even see very asymmetric behavior with respect to the bounce, if you choose asymmetric internal clock with respect to the bounce. And of course, there's let's say a full relativity in this picture, because the quantum variables, or these observables, are natural from the point of view of this initial clock. So with another clocks, you will see this, let's say, crazy behavior. But if I choose canonical variables and the respective quantum operators associated with this choice of clock, this dynamics would look very nicely, and the dynamics in this clock and in this clock would look very crazy. Yes, there is no preferred choice of clock. So there's no standard like simplicity by which you can say that one clock is better than another. But there's a very important feature that irrespectively of what happens here, you always have a bounce, and this let's say classical state will always end up, this classical state, as this classical state, away from the boundary where the quantum corrections start to play a role, at least at the semiclassical level.
Is there any possibility to choose such an internal clock that this line will be straight?
Will it be straight? You mean
Trajectory will be straight.
will hit the singularity?
Only.
No, I don't think there are some unhealthy choices, but there are some technical, let's say, conditions, mild conditions, which you have to impose on the clock transformations. So this can be probably obtained by some unhealthy choice, but I don't know whether you will get unitary evolution and so on with this choice of clocks. So there may be some other problems. So I think that
possibility also that this T function, which is a shift in the clock, could be dependent on the original previous time.
yes, it can be. Here I don't consider it for simplicity, because everything is computable in one line almost.
Do you have a picture for the classical interpretation of the various choices of time?
In terms of metric?
No, in terms of slicing. In the original.
Yeah, but the slicing is very abstract from the point of view.
Yeah, I mean, just
It's not a slicing that you have in a space-time. It's a slicing that you have between different solutions.
I understand, but it may have some contact with the freedom you have in
choice. Soon I will show maybe a few delay functions. So maybe this would be useful. So I wanted to point that irrespective of what happens here, away from the bounds, that you don't expect any quantum effects to play an important role, you'll get at the same classical state. So there is some predictability. There's something which doesn't depend on the internal clock. It is the asymptotic behavior described in classical terms. Okay, here is a simple phase space. It's just, two-dimensional. So you may say it's just an artifact of the simplicity. So let's go to a higher dimensional phase space and consider anisotropic model, intrinsically flat. So you have 3 different scale factors. So you have so here's the constraint surface, and again I will fill it with a fluid. This is a constraint surface. You have the momentum of the fluid. This is the, let's say, position of the fluid T. So k squared is the usual p plus square plus p minus square, but they are constants of motion, so it's better to work with this parameterization k, and pk is a canonically conjugate, and it describes the change of the shape of the spatial leaf, yes, the ratios between different scale factors, pk. So here is the induced to form. So you take this symplectic form, again you solve, you get rid of this pt. So h is just this. This is the physical Hamiltonian, and the parameterization of the constraint surface is t plus the remaining canonical variables. Okay, and here you can also find the Dirac observables. You can consider pseudo-canonical transformations with the delay function, generic delay functions, but again, there should be some mild conditions on this. It's a technical issue. And then you will find new q bar and p bar. For d equals 0, it will be just q bar equals q, p bar, and this is new p. Okay. K is a constant of motion, it's a Dirac observable, so it doesn't change under this transformation. This is the classical. I discussed this yesterday, but let me repeat the most essential features. So this is the classical dynamics. The classical dynamics takes place in two branches, contracting branch and the expanding branch. So this is, let's say, volumes, and this is the expansion. In between, there is a region. It's a topological feature of the constraint surface. It doesn't depend on the parameterization. There is a region where classical dynamics doesn't occur. So, in a sense, we didn't fully deparameterize the model. In a sense, here is how this shape function, as I call it, pk. These ratios between scale factors behave as you approach the singularity. So you have these two types of singularities, the cigar-like and barrel-like singularity. So it blows up. Now when you quantize the model and you look at the behavior of expectation values of the respective quantum observables, you will see that there will be some crossing through this classically forbidden region, and the contracting branch will be connected to the expanding, and you will get a bounce. Also, you will have a regular behavior in this shape function. And now I will so we extended the phase space, and we see now what happens. So we go to another choice of clock by a delay function. Here is a delay. So delay function depends on my QP variables. So in this region of QP, I shifted the initial choice of clock by some function, okay? And it led to the following effect if I look at the dynamics of this expectation values in QP plane and a QPK plane as well. So this actually, I think that if I remember correctly, the technical issue is that you have to impose something on the delay function at the boundary. If you mess with the boundary, then you can obtain some ill-defined theory. But this is a perfectly well-defined transformation of the clock. Here's another example. So in this region of PQ, you shift your initial internal clock, and you see that there is some, of course, effect in terms of the expectation of the behavior of the expectation values. And the same happens in the QPK plane. Here's still another example, some kind of oscillatory delay function. So you get some kind of oscillatory, ugly behavior in this QP. But they will never cross each other because it can't. And here you will get some very strange behavior. Because from the point of this internal clock, it is simply a very unnatural choice of operators to describe the quantum dynamics. And here's still another choice in this region. Okay, so now I'm getting to the conclusions. So I propose what I call internal formulation of quantum mechanics, which accommodates the notion of clock transformations as an extra symmetry, and it led to some set of postulates which slightly extend the usual formulation. But it turns that many properties of the quantum dynamics depend on the employed clock, and if you like spectra, and if you go to cosmological systems, the number of bounce, cosmological bounces, the scale at which the bounce happens. But I try to convince you that this can be reconciled with the ordinary formulation of the quantum mechanics. And this has been achieved by splitting the system into two parts: internal observer, described approximately by classical formalism, and internal system described by the fully quantum formalism. And then we can speculate. Now you need to somehow understand it, to interpret it consistently, give some physical interpretation. And well, I would speculate the following: that if the universe is assumed nowadays to be an asymptotic, let's say, future state of and classical, everything is describable by classical formalism of a quantum system, then what I showed you is that the past, but again, it must be a classical state, the past asymptotic classical state can be determined uniquely, but nothing else, nothing that happens in between and when the quantum effects turn on. So in this very restricted sense, this quantum theory is a predictive theory, and quantum resolutions to the singularity problem are meaningful. But again, and this is in fact why this happens is quite easy to understand. It happens because we required that the Dirac observables are given the same operators irrespectively of the internal clock. This is a consequence of this assumption. Okay, I will finish here. Thank you for your attention.
I've got two questions. One is, the real universe is equipped with a natural clock. I call it the cosmic microwave background, which defines a certain frame of reference,
yeah,
and
but you're talking
time associated with that. So you're shaking your head. Good.
So no, it's not, because the notion of internal clock is it's a richer concept than the concept of time coordinate for a given space-time, which we are talking about. Because here you set a simultaneity between different solutions to the Einstein equations, between different space-times. And this has to be done if you want to introduce, quantum formalism. What do you mean a fluctuation? Quantum fluctuation with respect to what? And so on. So in fact, all these cosmological models already assume that there is a preferred. The examples I considered already assume that there is a preferred slicing in each of the solutions, because they were spatially homogeneous and isotropic. But still, that remains a freedom in setting the simultaneity between different solutions, different universes.
I understand. I'm just making the comment that the fact that our universe is equipped with a preferred frame is a non-trivial fact. So the next question I had was, in the cosmological models you studied, you assumed certain symmetries, homogeneity in particular. And I wonder, what is the role of quantum decoherence? Would a bounce survive quantum decoherence?
Well, I didn't consider this, so I don't want to make any...
Would you like to speculate?
Well, maybe...
If I said I don't think the bounce will survive quantum decoherence, would you dispute that?
The bounce wouldn't survive quantum decoherence. That I wouldn't... endorse this kind of statements because I don't know why should it happen, but I don't want to enter this.
Incoherence acts kind of like a frictional term, effective friction.
Mm-hmm. I cannot tell nothing about this at this point, but it's good to know.
It's a very impressive and nice setup, I mean, to understand things in a clear way. But as usual, the evil stays in the details, and you know the spectra and the dots. No, just
You're talking
on the last graph. You know the dots. They use boundary conditions and the choice for this elliptic operator, which tells you this spectra and how to define the base for your quantum system. It's really important, and there may be. I mean, my question is related to the fact that have you explored all the possibilities which are allowed by the setup you apply here to investigate, you know, whether this is
I consider that
degenerate, you know, behavior you get, or
I mean, there's a general formalism behind this, and of course, I explored only a limited set of examples, yes, to see what happens, yes.
I'm thinking about the mathematical setup, not the application.
Okay.
You know, this was, but what about this ingredient in the whole?
But which ingredient you talking?
You have to define your Hilbert, and you start with the Hilbert space, and then you define some sort of elliptic operator which helps you to.
But you're talking about specifically about a model, a cosmological model, like.
No, not a cosmological model, but the whole setup, and then you define. You start with the Hilbert space, and then you have an elliptic operator on that. What is the and you had some sort of boundary conditions also for your system. So
No, but I was talking about the boundary of this particular system, a particle on a half-line. That's what you are referring to?
Yeah.
No, if I understand you correctly.
No, I mean, but
because I don't.
But your elliptic operator also.
But which?
Have some freedom, no? I mean, I'm just.
You mean now you're talking about this operator? I'm sorry about. No, you're talking about this D operator, which
There was some elliptic operator at the very beginning of your generic construction.
Okay, we can look for it.
And you had a spectra.
So spectra appear only in the example of a free particle and the position. So it's here. It's here, and you have a fixed state, and then you describe the associated probability distribution in terms of the. So now maybe your question is that if I go to another internal clock and find that the same observable corresponds another operator, maybe the operator is not self-adjoint or something. This may happen, of course. So you maybe have to fix some additional boundary conditions, or maybe it cannot be made. There can be such issues. So usually what I do, I confine to such examples where it works. But in full generality, of course, there will be some problems with some transformations, internal clock transformations.
My question was really to allow and mathematically fitting choices have been explored or not. How could this change the picture?
So all I have is some example to build a picture of how this internal clock influences the dynamics. But I'm pretty sure you can explore it further and arrive maybe at some nice general statements, which I have not arrived at yet.
Okay, let's thank the speaker again.